There is hope, though, in defending the network. There are some very good solutions that have to do with strengthening the protocols, reinventing the protocols, or engineering software or hardware in order to stop computer network attacks. We will review these in the next couple of videos. One of the biggest defenses for the security of our application layer is what we call the secure socket layer, which is what our HTTP secure websites are based on. Through a handshake, we establish a secure communication, exchange keys, and cipher specifications, and then we can exchange data securely because the secure sockets layer is encrypting everything after the initial handshake. We'll get into the details on the next couple of slides. So as you can see here, the detailed messaging that happens when you establish an HTTPS connection is shown in this slide. And you can see that initially the client that initiates the connection, that let's say wants to talk to Amazon.com, is sending a list of ciphers that it can use, and also is sending initial information, the version of HTTP that they're using, and things like that. The list of ciphers is a little tricky because we see in these ciphers still a DES, for example, appearing, and as you know from this class, DES is no longer safe. So when the initiation happens, the second message is from the endpoints, the server, let's say Amazon. They are going to send their certificate, and therefore the client will verify that this is truly Amazon. And we have already discussed about certificate authorities that help us, that we trust, and they help us verify that there's a server that is trusted and it has a valid certificate that has not expired. Then the next message is a message from Alice to Bob, from the client to the server, where the client is using a random number to send to Bob, encrypted with Bob's public key. So in this case, we're using public key cryptography or Diffie-Hellman to exchange a key that will then be used with secret key cryptography. Because as we have said, when we're doing crypto, public key cryptography and Diffie-Hellman are very expensive. We need to find these really large, very special type of prime numbers to use it. So we don't want to do it over and over again. And so we only use it to exchange keys, and then we use secret key cryptography for the rest of the communication. So both parties derive a key with those random numbers that have been sent with public key cryptography, and then communication can start with secret key cryptography. So this E key and data is secret key cryptography that has been used to ensure that communication is confidential. When we were discussing about cryptography, we discussed about certificate authorities and how public key cryptography is used to sign certificates, and hashing is also used to make sure that they have not been tampered with. And we explained all of these different things. And you also had a homework assignment on digital certificate authorities. Now, the problem with certificates that we did not discuss is trust. How can we make sure that a certificate authority is trusted. Of course, we said we are signing the certificates using public key cryptography, and we're also using hashing for the integrity of the message. But the other thing is, what if the certificate authority is compromised, or if they are not doing the right job handling on certificates? Then we are in trouble. So there are issues with centralizing something like certificates. There are validation authorities that provide information on behalf of the certificate authorities, and there is a whole management system, but still it's fairly fragile because there could be issues with certificate authorities being compromised. So to conclude with this SSL, we are targeting the application layer with SSL. We're targeting the confidentiality and integrity of the data in the application layer. And we need to bear in mind that because it's the application layer, applications may not abide by these rules, and they may destroy whatever SSL is trying to build. For example, in smartphones, applications do not verify certificates correctly, or they don't verify if they have expired or not. And that, of course, can have implications because you may be trusting a website that is no longer valid or no longer should not be trusted. And of course, developers change default configuration, and you can think about different reasons why they would be doing that. Could be ignorance, they may not know how default configuration works, or it could be purely usability or something along those lines. Applications are a very variable ecosystem, and so even though SSL is doing a great job certifying our data and keeping it confidential, on the other hand, an application developer could cause trouble if their application does not abide with the principles, the security principles.